So, good afternoon, everyone. Slightly louder, please. That's better. So, before I start this talk, I want to clarify a bunch of things. There is a lot of content written on the slides, but you are not supposed to read all of that right now. Okay? That is to be used as a reference material when you go back to your places and you want to dig more into it. Okay? What I will do, I will try to verbalize my thought process for this attack. You are supposed to focus on the thought process, not on whatever is written here. Okay, that is only reference material. Is that clear? Yes. Okay, so the topic is rather strange looking. We are going to deal with containers, typical Docker containers, and we will try to breach the container boundary, as in we will leak some data from container A to container B using side channel. Generally, you do it via misconfiguration, via some exploit, something like that, but we are not going to use any of that, okay? So this is the agenda. I will start with my introduction, then we will talk about some motivation, as in why someone would like to do something like this. Then we will revisit container internals, some stuff about CPU, instruction set, power consumption, how physical layer communication happens, how a side channel is designed. Then there will be a recorded demo. And then we will talk about test setup that you can probably replicate if you want. And then we will briefly discuss possible detections and countermeasures. So this is my introduction. I am Adhokshaj Mishra. I work as security research lead in an EDR company. I mostly focus on breaking things. As in, I am not the guy who will tell you how to stop some bad thing from happening. I am the person who is going to tell you how to make bad things happen. Okay? I go in opposite direction. I mostly dabble into offensive side of malware, little bit of applied cryptography. I used to dabble in cryptographic backdoors as well, that I don't do anymore, mostly because of limited time. I am a hobbyist programmer. I don't write code for my profession. I just do it because I like writing code and automating my stuff, okay? I mostly care a bit too much about FOSS, even though I am using a MacBook, which is not really FOSS. My guilty pleasure, setting things on fire, breaking things apart, and making other people go nuts. And we can connect over LinkedIn. Username is here. This is a typical boilerplate disclaimer. Whatever I am going to teach you is only for academic interest only. So do not repeat it without proper authorization in place. And if you do it and land in hot water, then come to me that, hey, Mishra, I did what you talked about, and now I am in complete mess. I will be like, okay, I don't care. So now, we come to the motivation part. How many of you have heard about the phrase side channel attack? Just raise your hands. Is it because of Meltdown and Spectre? I suppose most of you heard about it during Meltdown and Spectre. Okay. Have you heard about Fan-smitter? Okay, so some years ago, there were a couple of researchers who leaked data using noise generated by the cooling fan found in your computers. Okay, that was pretty fantastic research. That got shared a lot, and then it came to me. I made a comment saying that, okay, bandwidth is going to be pretty crap. So it is good as an academic exercise, but practically it is not really useful. And then someone was like that, okay, you are saying this because you cannot pull something like this off. I took the bet, result is here. That is one part of the motivation. Second is containers are way too popular. How many of you deal with deployment side of things? Infrastructure type stuff? A lot of you. Probably you also deal with Docker and Kubernetes. Please raise your hands. Fantastic. How many of you are developers? Quite a bit of you. Nice. So probably you also want to ship your machines. You have a bug, but stuff is working on my machine. So I will just clone my machine and give it to you. Ergo, the biggest use of containers. And then there is this point of having at least some sense of security, because you are basically isolating processes across certain boundary, and then you get this feeling that, okay, it is isolated, therefore it is a bit more secure. Fine? Now, since containers are also getting monitored for security incidents, maybe you use something like Sysdig, Falco, or some other bunch of tools specific to either containers or Kubernetes or cloud-specific stuff. Many of you will be probably already doing this. The problem is that if it is getting monitored, I cannot really have too much fun. If I try to have some fun, I will be busted. I do not want to get busted. I want to have fun. Okay, that is my motive. Then side channels are pretty sexy things. They give me social brownie points. I get bragging rights. Bro, you only write exploits for misconfiguration? Noob. I make side channel attacks. Me legend. Okay, and last point is, it is extremely difficult to monitor for side channel attacks in general. So there is no specific tool or specific technique that can protect you against side channel attacks. Now we will go with very quick recap of containers. Most of you probably already know it is mostly a set of one or more processes which are basically isolated from rest of the system. It allows us to partition resources. It allows us to set some sort of policies that our container can use only 20% CPU or only 100 Mbps bandwidth, something like that. And obviously, it allows you to ship your machine. It works on my machine, take my machine away. And that also means that at deployment time, you don't really have to deal with headaches. You don't really care about which version of glibc is installed on Ubuntu or Debian or CentOS or something else. You're just like, okay, this is the image, Docker pull, Docker run, be done. Now, because of scaling, this became really popular. And second reason is that for some reason, people really like to replicate Google, whether it is applicable or not. So Kubernetes it is. And it also has a lot of easy to use tooling. Docker is really easy to use. There are 1 million write-ups, so everyone is learning Docker. And obviously, it is popular everywhere, which means if I target containers, I have a lot of targets to pick from. If my stuff does not work at one place, probably it will work at some other place, and I will end up doing something fun. That is my last motive. Now, this is how we start a very simple container which has absolutely nothing fancy going on here. Ubuntu image, bash as a startup process, and we get a bash shell. This is something that you do once you start learning Docker container. The step one is paste this command, docker run it image name and process name, and you get a shell to do something, whatever you want to do, right? And obviously, there is nothing shared between host and containers, okay? I have not shared any path, any volume, anything, nothing. It is just completely isolated container, or at least that is how our write-ups and blogs try to portray it. They show you this command line. They say that in command line, nothing is shared. Therefore, nothing is actually shared, but there is a catch. If I do something like this, what I am doing here, that I am accessing some particular temperature sensor, and I am getting some reading out of it, okay? Now, if I do the same thing on host, what ends up happening that I am getting exactly same value inside container and outside container. By the way, this thing does not happen in virtual machines. In virtual machines, the sensors are virtualized and they basically give some dummy values. They don't give you actual readings, but it is not the case in containers. Which means, if somehow, I don't know how, if somehow I can manipulate the sensor into giving a reading that I want it to give, I can twist and turn this into leaking data. Does that make sense? Okay. So my biggest problem is somehow controlling this thing and controlling this thing little bit reliably. If I am able to pull this off, this is going to work. Okay? So now that is my reaction basically when I was doing this. Now we come to some little bit of basics part. Most of you studied about CPU in school, that this is a tiny chip that does all the brainy work in computer. And you learned about instruction set most probably in your undergraduate courses in engineering, when you were learning assembly or something like that. Is that correct? But did someone tell you about power consumption thing? Yes or no? No one talked about it. And that is the fun part. Fun part has been missing so far. So this is a very quick rundown of CPU. You already know it. I will skip it. Instruction set, it is basically a complete set of all possible instructions. There are different types of instruction sets that you can catch up at some other point of time. And now we come to the fun part that has been missing so far, and that is power. There are a bunch of thumb rules. One is obviously the more work you do in per unit time, the more power you are going to require. Okay? Similarly, the more complex your instruction set architecture is, the more power you need to actually run it. Okay? And even in instruction set, if you pick some instruction which is doing a lot of convoluted stuff in one go, it will generally take a lot more power than some other simpler instructions. The only problem is that if you keep doing it for a long time, CPU does not really like it. How many of you have heard about speed step and turbo boost? Just raise your hands. Speed step. Very few. Turbo boost? Okay, how many of you have seen shameless promotions from CPU vendors? My CPU runs at 2.4 gigahertz and up to 3.2 gigahertz. So if you go below 2.4 gigahertz, that is underclocking, that is done by a speed step. And if you go above 2.4 gigahertz, that is overclocking, that is done by turbo boost. Okay? The problem is that CPU does not really like getting too hot. Okay, if it goes too hot, it will immediately shut itself off. So that also means that we cannot really do it for very long time. Now, second piece of the puzzle, physical layer of communication. And communication is something that many of you probably learned about it in your computer network subject, most probably in undergraduate course of computer science. You learned a bunch of different protocols. And then physical layer communication was just, oh yeah, there is something happens at physical layer. We will move on to some other topic now. That is what happens, correct? At absolute best, you probably heard about something like Manchester encoding, but then that is the end of physical layer communication. Am I correct? Okay, so we will cover this into a little bit more detail. So now suppose I want to transmit some bits, okay? A very obvious approach can be that I set two values, that whatever it is, it may be temperature, current, voltage, whatever it is. And I can say that, okay, if I set this value to high, for some definition of high, I will consider it as 1. And if I keep it low, I will interpret it as 0. Okay, this is very simple stuff. And now if I want to transmit something in sequence of zeros and ones, I can keep varying the levels between high and low, and I can read it at other end and then recover zeros and ones out of it. Okay? Good part is it is very easy to implement, very easy to understand, but will it work in practice? What do you think? Or rather, what do you think should happen? What is your intuition here? Should it work? Will it work? Or is there some catch and there is some sort of devil hiding somewhere in the details that we are unable to see? Anyone? Any guesses? Sorry? I did not get you. Yes, that is a problem. If there is a continuous stream of ones or continuous stream of zeros, we have a problem. We will eventually lose count of it. Maybe I am transmitting 4 ones and I am getting only 3 ones or 5 ones. So that is a problem. And this is because of timing. Okay, I am keeping some sort of time delta, and if timing is getting out of whack, I will either miss data or I will try to produce data out of thin air, and both of them are wrong. Okay, now an ideal clock does not really drift, but in practice, no matter which clock you are going to use, it is going to drift. Maybe it will slightly go faster, maybe it will go slightly slower, maybe it will bounce between faster and slower, or do something equally funny, but it is not going to maintain constant ticking rate. Which means that as an engineer, we have to figure out how to deal with it. So now the problem statement is that we are having timing issues because we are having 2 different clocks at both ends, okay? Now someone can come up and say that, okay, problem is because we have 2 clocks. What if I take only 1 clock, wire it at both ends, and then transmit? One obvious problem is that if the range is rather long, then you can't really wire same clock at both ends. But even for short durations, it is not really going to work. Okay, and the reason why it is not going to work is because of timing skew. Okay, now a quick question. How many of you have seen PCBs, printed circuit boards? Many of you. Have you paid attention to the traces that you see? Many times, instead of taking shorter route, some of the traces will go and take rather long route for some reason. And at some other instance, you may see some sort of squiggly lines. Trace is getting straight, then bunch of squiggly lines, then it is getting straight again. Have you ever wondered why? What is the purpose of those squiggly lines on the PCB? Or why are we routing it, taking much longer route than optimally needed on the PCB? Ever thought about it? Do you know the answer?
Delay.
Sorry?
Delay.
Yes, you want to set both wires of signal at same length. Okay, if there is mismatch of length on one end, you will get one part of the signal faster than the other, and then you will run into issues. So that is basically timing skew. Now, there are different types of clocks. There are S-triggered, there are level-triggered, but the problem is that you have to deal with skew. So we cannot really take one clock and wire it at both ends. This is really not going to work. Okay. Now there will be a bunch of violations. You can search about these phrases on internet and read in more detail because these are more complex than really required here. Now, we cannot have 2 separate clocks. We cannot have 1 clock wired at both ends. So what is the option that we have now? Anyone willing to take any guess? Sorry? And how exactly is that going to solve timing problem? Okay, here's the solution. We throw the clock away. We don't really need a clock. And we don't need a clock because self-clocking signaling is a thing. And it works like this. Suppose I have a signal of constant frequency. It can be 1 hertz, 10 hertz, 100 hertz, whatever. All I am saying that this part of signal will maintain this specific frequency for entire duration of the communication. Which means if I generate that constant frequency at one end, you can capture that signal at other end, figure out its specific frequency, and then use that frequency as clocking mechanism at other end. Okay? Now, the problem is that you can send timing information this way, but now you can't really send any data with it. Earlier, we were able to send data, but we were not able to send timing. Now we are able to send timing, but we are unable to send data. So what do? we basically do modulation, and it is something that probably you heard about during your school years, or maybe if you are familiar with old school radios, there used to be two settings, amplitude modulation and frequency modulation at least. So this goes back to the same part. And now what we are going to do, that for timing, we need frequency to be constant, okay? Which means for data, we cannot change frequency. Which means I can change either amplitude, that is amplitude modulation for same frequency, or I can change the phase difference of the signal. There are two options. Now, we are not really going to do this amplitude modulation because that signal quality becomes really crap, which you will know if you have ever tried to hear something on amplitude modulation radio over long distances. Voice starts crackling, right? So we can't really use that, which means that we have to rely on that phase modulation. And for phase modulation, there is one specific scheme that is used at too many places, that is called binary phase shift keying. If any of you are from electronics and communication background, probably you studied this. For computer science, maybe you studied, maybe you didn't, depending upon the school you went to, but this is covered in electronics and communication. Now, if you have heard about Manchester encoding, you just need to know that Manchester encoding is one specific case of binary phase shift keying. So for this specific purpose, what we are going to do, we are going to stick to Manchester code because this is taught basically everywhere, okay? Now, for Manchester code, there are two different standards. One is IEEE, one is G.E. Thomas, and basically the interpretation is opposite. That is the only change. Here's an example of Manchester code. On top, you see the clock signal at a specific fixed frequency. Below that, you see the data signal. And then you see that phase modulated signal that is getting transmitted, okay? Now, we are able to send timing information. We are able to send the actual data that we want to transmit. But the question is, how do I know when transmission started? And how do I know when transmission stops? Because that timing signal is consistent. I keep getting data, I keep getting signals, but now I do not really know when to start recording the data and when to stop recording the data. Is the problem statement clear to everyone? Okay. Now, there are a bunch of options. One is we can do out-of-band signaling, as in we can have yet another signal, which basically tells that, okay, data transmission starts here and data transmission stops here. But the problem is that now we need two separate channels instead of one. And engineers, being engineers, don't really like to do hard work. They are pretty lazy species. So what they do? They do something called self-synchronizing code, okay? Earlier we had self-clocking signaling, and now we have self-synchronizing code. Basically, we take same channel and we do every goddamn thing on the exact same channel, just because we do not want to deal with two separate channels, because we are lazy, okay? So, a self-synchronizing code has a very cryptic definition in computer science, but the basic idea is that you take two magic sequences, okay? And the only condition is that those magic sequences should not translate to any valid data. Which means even by mistake, you should not be able to decode any sensible data out of these two magic sequences. Once you have that, you say that, okay, sequence 1 is the start of the transmission, sequence 2 is the end of the transmission. And whatever happens between start and end is your actual data. Make sense? If you want an example, probably you are familiar with Unicode. How many of you have dealt with Unicode? A lot of you. How many of you cried while dealing with Unicode? Many of you. And you cried because it is variable length encoding. You don't know whether you have to read only 1 byte or 4 byte or maybe more than that. Correct? And for that, if you want to separate between glyphs, you have to basically rely on magic markers in UTF-8 as well, 2 of which are given here. These are used to denote that, okay, this is where one character boundary stops and next character is going to start. So this is an example of self-synchronizing code. Now, since some wise man once said that devil is in details, we are yet to get rid of that devil, and devil is called noise. Okay, we figured out timing, we figured out data transmission, we figured out synchronization, and now we are dealing with noise part. And concept of noise is really simple, okay? Suppose we have this hall, I don't have mic, and all of you are talking to your immediate peers. There will be too much noise, and if I try to say something, most of you will completely miss whatever I am saying. Even if you try to focus on what I am saying, you will not be able to make any sense out of it because all the noise is getting jumbled up and it stops making sense. That is noise for you, and that is what happens during transmission as well. This is an example. On top you see original, really nice looking clean signal, and then you see noise, and the result is some sort of garbage like this. And the problem is that we have to deal with it, and we have to somehow extract the topmost signal from the bottom-most signal. Okay? Now, how many of you are afraid of theorems for whatever reason? Maybe you did not like writing proofs, maybe you hated theoretical aspects of computer science or communication. Please raise your hands. Only one? Rest of you really enjoyed writing proofs? You are laughing. That means you did not enjoy writing proofs. Okay, so here we have this problem. And now we have some really amusing theorems. Okay, first one is Shannon-Hartley theorem. It looks, again, rather mathematical with a lot of specific meanings, units, dimensions. Again, we will not go into that right now because this is reference material. The basic idea is this. For any channel which has some amount of noise, where you can measure the overall power of noise and signal, this theorem basically tells you the maximum theoretical bandwidth that you can achieve under presence of noise. Which means that as long as you transmit below that maximum frequency, that maximum bandwidth, you will be able to eventually transmit all the data that you want to transmit. The only condition is you do not breach the bandwidth. Okay? That is one part. Second part is this neat little theorem, and this says that for any communication channel which has some amount of noise, again, you should be able to quantify how much noise is there, how much signal you want to transmit. It basically says that it is possible to transmit data in such a way that you get arbitrary amount of accuracy. See, here, because of noise, our signal is not clean anymore. Okay? Which means that if you try to interpret under presence of even stronger noise, you will end up misinterpreting the original signal. Okay? This theorem basically says that there exists some sort of scheme. It does not give you exact scheme. It only proves presence of such schemes which allow you to recover the original signal from noisy signal. Okay? First one gave us maximum bandwidth. Second tells us that somewhere out there in the world of communication theory, there is some scheme which will allow us to transmit data without any errors. But it does not tell you how to do that in practice. It only proves presence of such schemes. And that is why people hate mathematics. A mathematician will come and say, okay, I prove that there exists something like this. And then you ask, okay, how do I do it? Meh, I don't care. Now, once we have established this, there was a lot of work on this error correction mechanisms, and these are called error correction codes. These are basically extra bits in transmission which do two things. One, they tell you if there, basically they do three things. One, they tell you if there is an error. Second, they tell you which bit is incorrect. And third, they allow you to recover that bit. First, you need to know that some error happened. Second, you need to know exactly on which bit that error happened, and then you need to figure out how to correct that error. Okay? These three things are done by error correction codes, and again, there are a bunch of simple looking to very strange looking mathematical things which allow us to do it. We will not go into nitty-gritty of that. You just need to know that there are basically two types. One is block-based code, where you need some block of data. And then you put error correcting code for that entire block. It cannot do for something that is smaller than a block. And then there are continuous codes which can be used in some sort of streaming system, right? So for examples, for block code, there is something called Hamming code, widely covered in computer network courses in universities. Second one is convolutional code. Maybe you read about it, maybe you didn't, depends upon which book you picked up. Now there are some more examples. For example, Reed-Solomon code, convolutional Hamming, we already covered. And now we have basically all the bells and whistles to deal with all the devils in whatever we are going to do. So now the only one problem remains, and that is design of covert channel. And which means we are back to controlling that temperature sensor. Okay, if I want to say, if I want to make it to say A, it should say A. It should not say B. Okay. Now, for definition, a covert channel or side channel is basically some sort of unintentional channel that is not really supposed to exist, but still somehow exists because we are not in a perfect world. And then these are a bunch of elements. First, you need some parameter that you can control. It may be voltage, it may be time, it may be noise, it may be fan speed, it may be CPU frequency, it may be something else. It may be presence of file, it may be size of file, it may be voltage on RAM, whatever you think. As long as it is controllable, we can use it. Okay? Then you need some mechanism to control that parameter with respect to time. Here we need something which can be controlled. Then we need some mechanism which allows us to control that parameter. Then we need modulation, demodulation, clocking, synchronization that we already covered. Those are already solved problems. We just reuse it and move on. Now we are here. This is the crux of the talk, and that is temperature as covert channel. Now, what is the parameter here? The parameter is CPU temperature. Okay? Control mechanism. I am going to stress the CPU, trying to make it do a lot of work in very small amount of time, which will force it to use a lot of power, which will eventually result in a lot more energy wastage, which will come up as heated CPU dies. Okay? And if I remove that stressing code, it will eventually cool down back to its normal range because our computers have heat sinks, thermal paste, fancy fans, liquid cooling, bunch of other things. Modulation, demodulation, clocking, synchronization, you are free to use whatever scheme you are happy with. It doesn't really matter. Now, I want to stress the CPU, which means, going back, I need to find some instructions which do a lot of work in teeny tiny amount of time. Okay? There are a bunch of extensions supported by Intel chips and AMD chips. Now, here again, we have a bunch of thumb rules. Basically, it is reiteration. You need to do a lot more work in little bit of time. You need to pick very complex instruction sets. And even in that instruction set, you need to pick basically most complex instructions. Okay? Now, for Intel architecture at least, instruction sets generally increase in complexity with time. Newer the chip, the more complex instruction set it tends to support. CPUs mostly run underclocked, basically to keep them cool and to, in case of laptops, to reduce their power utilization, which results in longer battery backup. And power consumption is roughly proportional to third power of frequency. So if you double the frequency, power consumption becomes roughly 8 times. Okay. Now what we are going to do, we are going to use AVX instruction set because that is the maximum I could do on my Intel laptop. And to find exactly which instructions to use, what I did, I basically picked a bunch of instructions at a time and I ran them in a loop, trying to figure out at what time I am seeing how much spike in temperature. And with a lot of trial and error and guesswork, I eventually figured out these things which seem to work rather nicely. How many of you studied assembly language in your college? How many of you still use assembly language in some capacity? Maybe reverse engineering, maybe exploit writing, shell coding, anything. Raise your hands. Have you ever used any of these instructions? Exactly. Now, for first instruction, it does a lot of things. It will take double precision floating point values from two huge registers. It will multiply, pack them, add to third register, and then put result into some other register. And similarly, all these three instructions are doing it. Okay, based on the description that I have given here for first instruction, what do you think is the use case for this? I mean, Intel will not be that stupid that they will be like, okay, we need to do something. Let us add one more instruction to do something, whether it makes any sense or not. So the question is, what is the intended use case of this? Anyone? And AI came way later. Exactly. These instructions are rather heavily used whenever you have to process a lot of graphics stuff. So most of the time you will see these things in your gaming engines, in your video processing units, that sort of stuff. Now we have instructions, and now we have to take opposite track. We generally read about optimization things. We want to optimize for memory consumption. We want to optimize for load on CPU, for storage, for bandwidth. But here we need to go opposite. We want to de-optimize it as far as possible. Because we do not want to run the CPU cool. We want to run it hot as it can go. Anyone? Any ideas? Take a wild guess. You have learned about optimization, so you know what to do. You have to just go against those wisdoms, and you end up with this. Now, again, there are a bunch of pro tips. You can do a lot of floating point arithmetic. It is costlier than integer arithmetic. Division is costlier than multiplication many times. And one practical advice is that if you want to do something like this, you need to pack multiple instructions in a tight sequence. You can't pick one instruction and loop around it. Okay, you have to pack multiple instructions, make a hot loop, and then loop that entire set of instructions to make CPU go hot. And since our CPUs are multi-core as of now, what we do, that we take same code, we run it on all the cores at same time. Now, doing this, we will be able to heat our CPU dice, but now we want to cool it down. Newton's law of cooling. Does it look familiar to you? Okay, you forgot. Probably in school you did some small experiment where you take boiling water in a copper vessel, wrap it in a wooden box, put a thermometer, and then you plot a graph that at time t0, temperature is this, t equal to 5 minutes, temperature is that, t equal to 10 minutes, this is next temperature, and then you get a graph something like this. Do you recall that experiment or not? You didn't do that? No problem, you can Google about this. So it basically says that the higher the difference between hot and cold, the faster it will cool down. This means that while I am trying to heat the CPU up, I should not heat the heat sink itself. If the heatsink itself becomes hot, the temperature difference between the CPU and heatsink will be much smaller than I desire, which means that CPU will take long time to cool down. And I don't have that much patience. I want this to go fast. Okay? So here we have opposite constraints. On one side, I want to heat the CPU, but on the other side, I do not want to heat the heatsink, which is directly sitting on top of the CPU. Do you realize the weirdness of this thing? Now, this I already explained. We cannot keep CPU hot for long enough time, because then heatsink will become hot. And if we do it anyway, CPU will start throttling and it will refuse to heat up further, defeating the whole purpose. For cooling, logic is simple. We just stop running all those fancy and weird looking instructions and let physics do its thing. Okay, now here are the practical constraints. We should be able to heat the CPU by sufficient margin within 2 to 3 seconds max. Longer than that and our heatsink starts heating up, which we do not want. We have a timing constraint here. Similarly, CPU should be able to cool down back to normal temperature within 3 or maximum 4 seconds. Again, because I don't have that much patience. Okay? And heating and cooling should be reliable with respect to time. It should not be that, okay, this time I am able to heat it by 15 degrees Celsius in 2 seconds, but 5 minutes later it is taking only 1 second or taking 3 seconds for same temperature delta. This is not going to work. So it has to be reliable. And system load from all other things which are running on that same machine, they should be almost static. Otherwise, this whole timing thing will go for a toss. Now we have a lot of coding stuff. We design the hot loop that will stress the CPU. Okay, and now I have 3 different options. I can write directly in assembly. I can write in inline assembly and do rest of the code in C++ or C, or I can write using intrinsic. Since I am lazy, I hate working hard. Therefore, I do not want to learn the assembly aspects of those weird instructions, which means I am not going to use assembly. That also translates to I am not going to use inline assembly either, because again, I have to open that Intel developer's manual and read about those weird and cryptic looking instructions, trying to figure out which instruction is going to take which particular register. I don't have time for that. Okay? I want the compiler to do the heavy lifting for me. I only want to hint it to be, bro, please do this. I don't want to put any more effort than that. Okay? All we need, Linux box, that is free, and the glorious GNU G++ compiler. This is the basic setup. There are a bunch of 256-bit registers, and then I am storing bunch of arbitrary floating point values. The values themselves don't really matter. You can put any floating point value you want. And then for hot loop, I do something like this for all the registers that I have declared here. Okay. And this is done to ensure that the CPU is going to see a lot of AVX instructions tightly, one after another, one after another, one after another, so it does not have time to wait for something else and lose all the heat that it got from this. Okay. Now, for data I/O, what we are going to do, we will take data, convert it to sequence of zeros and ones, basically conversion to binary. Then we will figure out clocking, synchronization, Manchester encoding, and for that we will get a sequence of highs and lows, and then for high and low we will simply heat the CPU up or let it cool down. That is all we are going to do. For reading the temperature, generally this is the path. X and Y are integer values. On different systems, you will have slightly different values for same sensor. So before you do this, you need to figure out exactly which of the temperature sensors is going to tell you temperature of CPU. Okay? So you need to figure out that, then you just keep repeating repeatedly reading the value out of it, and then find the fluctuation and decode back, doing all the dance in opposite directions. Now for reading data, point number 1, it should sample temperature at more than 2 times frequency of modulation. Question, why? Why is there constraint of having sampling frequency being more than twice the frequency of modulation? Sorry? Nope. Nope. Nope.
Otherwise, you won't see the transitions.
Wrong. Okay, how many of you are from electronics background? Few of you. How many of you studied digital signal processing? Digital image processing? Okay, no one. Fine. There is a theorem called Nyquist theorem. It basically says that you need to sample at more than 2 times frequency of modulation if you want to recreate that signal reliably. And that is why when your headphone is producing audio output of roughly 20 kilohertz, your recording equipment is sampling the audio data at 44.1 kilohertz. It is following that Nyquist theorem. So if you ever studied digital signal processing or you want to look it up, you can pick those books, and this is very clearly defined there, that you need more than 2 times frequency of modulation. Otherwise, you won't be able to recreate the original signal reliably. That is why this condition is there. Rest of the stuff, demodulation, decoding, error correction code to figure out if some bits are wrong, correcting them, then recover original bit stream, and then you can turn it into whatever you want. Now we have demo time. Okay, so there are 2 screenshots and 1 video. So this is 1 screenshot here, and what I am doing, that I have 2 binaries basically. One is writer, one is reader. Writer will basically take data and it will heat the CPU and cool it down in some pattern. That reader binary will simply keep probing the temperature sensor, and it will try to recover whatever is being transmitted here, okay? So this is the recovery part. Here I am saying that, okay, recover 2 bytes instead of 1. And if you pay attention, the first byte is recovered perfectly, and then everything is 0 because there is no transmission after that. Okay, now I will show you the video. Okay, so here what is happening, that I have 2 containers. Okay, the only thing that I am sharing with container is the path where I have kept this reader and writer binary. Okay, because I want to run this binary from within the container. Because the whole premise is that we are going to breach the holy container boundary that is supposed to keep us safe. Okay, there are 2 containers. Both binaries are available in both containers. And now what I will do, I will read at one end, that right side, and write from left hand. And, okay, let us, if you see here, wait. Oh, okay. So here is the recovery part, and it will complete 16 bits and then exit. Okay, it is exited. Now the second part of the video shows fluctuation in CPU temperature. So I think I have run the sensor utility under watch. Yes. Now pay attention to this part here. This will keep spiking up and going down. $95, $100, $72, going down $70, $69, $68, back to $100, back to 75, and so on. So these two parts of demo are here. Nothing else is shared, and yet I am able to leak data between two containers which are on same host. Okay, so once we have this much, okay. Now the test setup, this is only for reference purpose in case you want to recreate this at your own end. So this is the hardware that I have used. This is the configuration that I have applied before doing this. This is the inner hot loop. These counts are basically number of times I have packed same instruction in the hot loop. Okay. So first one is packed 18 times, second one is 6, third one is 6, and this inner hot loop runs 210 million times per heating cycle. Similarly, there is an outer hot loop. Again, instructions and counts are given to you, and this runs for 210,000 times per heating cycle. And this is the data that I pulled out with some practical stuff. Time period for one heating cycle is approximately 2 seconds. Exact value is between 1950 second to 2050 second. As per observation, same for cooling cycle. It is programmed to be 2000 milliseconds, so that is exact 2 seconds. Temperature delta is roughly around 20 to 25 degree up, 20 to 25 degree down. This is the peak and average temperature deltas. Peak, the maximum that I am saying is 25 degree up. Average is roughly 20 degree up, and same goes for cooling period. Now, if you repeat this whole thing, there is no guarantee that you get exactly this value. Okay? This is only to serve as some sort of a rough reference guide. Your observation should look somewhat similar to this, not wildly different from this, but it won't match this one exactly. Maybe your fan runs much faster, maybe you have better heat sink, worse heat sink, the thermal paste is gone bad, or it is new, depends. It should look somewhat similar to this. Now comes detections and countermeasures. How many of you want detections for this? Please raise your hands. Bro, seriously? You want detection and countermeasure for this? Okay, there is no generic detection method, but again, I won't disappoint you. Most of the time, you have to do a lot of witch hunting, which means before you try to figure out any of this, you need to figure out your threat model first. It should not be like that, okay, I heard about side channel attack, so today I am going back to my home and I am going to hunt for side channel attacks. Okay, figure out your threat model. If somewhere in the threat model you see possibility of side channel attacks getting carried out against you, then and only then you start the witch hunt. Otherwise you escape it completely, because things like this, they look good on presentation stage, but they are not very practical. You do this, and if you want to transmit roughly 5 MB of MP3, it will take around 10 to 11 months of complete transmission. So this is useful only when the data you want to leak is very small and so critical that doing this whole dance is worth doing for that. Otherwise, any of this does not make absolutely any practical sense. And as I said in beginning, this is done only for social brownie points. That pesky Fan-smitter is not going to leak anything useful. But the researchers got fame. Oh my God, they leak data from Fan. Same goes for Spectre and Meltdown. In practice, if you start doing it, you will need a lot of time to leak very teeny tiny amount of data. And you need a very tight degree of precision to be able to do any of that at all. But Meltdown and Spectre happens, websites are up, cool catchy names are given, presentations are run, and news outlets go wild with the news. Oh my God, unfixable vulnerability. That is the primary reason why things like these are done. Now, the parameters, they may be anything. It may be electromagnetic interference. If you want to read about it, there used to be something called tempest attack. It can be LEDs. There was one paper where someone was able to leak data out of routers by blinking the LED in some specific pattern. It may be acoustic noise. There was one more paper which used acoustic noise to leak encryption keys out of laptop. It may be brightness of screen, it may be brightness of some LED, some other light, or maybe sound wave beyond capacity of human ear. And if you are reading the last point, there is a tidbit. A mic is a shitty speaker. A speaker is a shitty mic. Which means that if your target does not allow presence of mic, many times you can use their speakers as makeshift mics to capture some data. And that is something that has been done and published. Now, if you want to see detection for this very specific side channel, generally temperature fluctuation with time looks something like this. There will be variations, but it will not be all over the place. But if the side channel stuff is going on, instead of seeing roughly steady state of temperature, you start seeing wild fluctuations. And those are not spikes like this one. These are rather large and wide fluctuations. Similarly, one can use frequency instead of temperature. So under normal utilization, frequency will be all over the place, but most of the time you will be seeing spikes. But under this specific side channel, again, there will be, instead of spikes, there will be rather wide pillars of fluctuations. Okay? Now, for other parameters, you can probably monitor general state and see if something funny starts happening. Again, depends upon your threat model. Without proper threat model in place, don't do any of this. For countermeasures, sorry, bro, you are out of luck. Okay? But again, for this very specific demonstration, what you can do, that you can take this path, and you can block access to this path from your containers. Your containers don't really have any need to continuously read the temperature. So probably you can do that, but it will only safeguard you from this very specific demo that I have given here. For anything else, you are again out of luck. Okay? Now, the basic countermeasure is you need to restrict access to hardware. Again, that is easier to say and way harder to do, because that is how you end up getting bunch of different misconfigurations in your containers and Kubernetes infrastructure. Similarly, you can audit the system to figure out if something wrong has happened or some misconfiguration is there. But again, this is easy to say, very hard to do. Because if you try to do this and you say that, okay, I do not want to run my container privileged, but then the software vendor whose software you are using inside container will be like, sir, we need privileged container, sir. Otherwise, no support for you, sir. And the problem is, since you have burnt a lot of money to procure that goddamn software, you are going to suck it up and run the privileged container whether you like it or not. And that is why it is very easy to say for me that, okay, don't run privileged container, but in practice, that is not how things actually work. So this is it. Thank you for tolerating me. Thank you.
Thank you for that one. The whole sort of bite rate is a bit slow, but I like that. So I think we have time for like one question. Anyone there? No? Yeah, good one.
Hi, thank you for a very good presentation. You mentioned in the middle there when you were talking about the cooling cycle that the temperature of the heatsink of the processor actually matters. Mm-hmm. How well would you think that this method works in an environment where you don't completely control these? Say it's a machine that's shared with other processes running, so something else might be heating up your heatsink.
You forgot one important point. This is for social brownie points. Don't take it too seriously. I'm telling you, side channels are not supposed to be taken seriously. They are done for social brownie points. So I am trying to get some social brownie points. Why are you getting serious?
Thank you.